Have you ever wondered how your phone knows what you want to do before you actually do it? Like how Spotify recommends songs you didn't know you love, or how Google Maps predicts traffic jams on your route? This isn't just pure coincidence, it's machine learning. And today we're going to be diving into what machine learning actually is, how it's behind so many things we use, and what makes it so powerful. Let's rewind back to the 1950s. Computers back then were huge machines, barely more than calculators, but a mathematician named Alan Turing posed a question that changed essentially everything. Can machines think? This question laid the foundation for artificial intelligence. Fast forward a few years, and a computer scientist named Arthur Samuel takes it further. He believed that if computers had enough data, they could actually learn to improve their performance over time. Now, Samuel tested this idea by teaching a computer how to play checkers, and here's the crazy part. It actually worked. The computer learned how to get better at the game by playing over and over, eventually beating human players. This historical event is widely considered to be one of the first examples of machine learning. How does machine learning actually work? Now, I want you to imagine you're teaching a computer how to recognize a cat. The most effective way wouldn't be to tell it every single detail about cats, or at least it wouldn't be the most effective way currently in modern history. Instead, you would show it thousands of pictures of cats. The computer studies the patterns, like the shape of ears, the fur texture, and it starts to pick up on what makes a cat, well, a cat. In machine learning, we're giving computers a massive amount of data and letting them figure out the rules on their own. The more data we feed it, the quote-unquote smarter it gets. This learning by example approach lets machine learning systems make accurate predictions even with new data. Now, there are three core types of machine learning, each with its own style of learning. We have supervised learning to start off with. This is like studying with an answer key. The computer learns from labeled data, like photos labeled cat or dog, so it knows what it's looking at. Supervised learning is great for specific tasks like facial recognition or email filtering. For the second one, we have unsupervised learning. Here, the computer doesn't actually get any labels and it finds patterns on its own. It's like giving it a pile of images and saying, find the similarities. This type is used for things like customer segmentation, where we want the system to find patterns without labels. Now, lastly, we have reinforcement learning. Think of this one as trial and error. The model learns by trying different actions, getting rewarded for correct ones, and penalties for mistakes. This is how we actually train artificial intelligence for things like self-driving cars and game strategies. By now in this video, it's quite clear that data is the backbone of machine learning. Imagine trying to cook with only a handful of recipes versus learning from hundreds of dishes. The more diverse, high-quality data we provide, the better the machine learning model becomes. This is why so much of machine learning is spent through preparing and curating data, because if your data is flawed, your model will be too. One of the very well-known applications of machine learning is in transportation, specifically with self-driving cars. So think about what goes into driving. You're constantly processing what you see, making split-second decisions, and you're predicting what other drivers will do. Teaching a car to handle all of that requires a lot of machine learning. So first, self-driving cars are equipped with a huge array of sensors, cameras, radar, and GPS. These sensors collect massive amounts of data about the car's surrounding in real life. The machine learning model in the car then processes the data to understand the environment, identifying things like lanes, road signs, pedestrians, and other vehicles, of course. But identifying objects would just be the start. The car also needs to make decisions: when to stop, when to speed up, when to turn. This is where reinforcement learning comes into play. Self-driving cars are trained through countless simulations, learning by trial and error. Each time they make a correct decision, like stopping at a red light, they get a reward in the form of improved performance metrics. When they make a mistake, like failing to yield, they're penalized. Over time, the system learns to optimize for safety and efficiency. Now, machine learning also helps the car predict what's going to happen next. For example, if a pedestrian is approaching the curb, the model has to predict whether that person will cross the street. By analyzing millions of similar scenarios, the car's algorithm can make educated predictions, allowing it to respond proactively. Now, although machine learning is advancing rather quickly, people have many concerns about the field. For example, one big issue would be bias. Machine learning models are only as good as the data that they're trained on. So take, for example, a self-driving car that's trained mostly on data from sunny, clear conditions. It might not perform as well as in rain or snow, for example, or worse if the data reflects any human biases, like not recognizing pedestrians in certain clothing or body types. The car might make dangerous decisions. With all these challenges and opportunities, there's of course a demand for people who actually understand machine learning and can build responsible and effective models. This is where careers in AI and machine learning engineering come in. AI and machine learning engineers are the people who actually tackle these problems head on, and they're the ones who design the algorithms, train the models, and develop the systems so that the machine can be more accurate. Machine learning is a huge field, and honestly, there's still a lot to learn. I'm a computer science major myself, still working to wrap my head around a lot of these concepts, so I'm not really here to claim I have all the answers. I'm just sharing what I'm learning along the way. But if you're also on this path, then let's figure it out together. Thanks for watching. Also, if you're interested in diving deeper in computer science topics with me, hit subscribe. There's a lot more to learn.